In probability theory, randomness is modeled in two main ways, depending on the nature of the variable under study. The two primary categories are discrete and continuous random variables. In this video, we will explore some of the most common discrete probability distributions. Stay with me. Common discrete probability distributions. Hereunder are examples of common known discrete probability distributions, such as Bernoulli, binomial, geometric, negative binomial, hypergeometric, Poisson distributions, with respective parameters. P, one parameter for Bernoulli probability model. Binomial has two parameters, the number of trials and the probability of success, right? Geometric, one parameter. Negative binomial, two parameters. Hypergeometric, three parameters. Poisson distribution, one parameter, where this element is the condition when to use each these probability models under discrete random variable. Discrete, once again, is nothing but when the outcomes are distinct countable values, typically denoted as this 0, 1, 2, can be countably finite or infinite. What the typical concept here is, the possible values are distinct countable values for which we can model either two Bernoulli, binomial, geometric, negative binomial, hypergeometric, or Poisson distribution, as the case may be. In this video, we will learn about Bernoulli distribution, binomial distribution, Poisson distribution in detail. The simplest form of probability model is Bernoulli distribution, which is a building block for many other distributions like binomial distribution. So what is Bernoulli distribution? It is nothing but representing a single trial with two possible outcomes. It can be success or failure. In practice, we come across with these experiments. For tossing a coin once, the outcomes can be fitted into Bernoulli distribution, because from coin toss, we expect to have either head or tail. Now, the random variable x can be 1, meaning that getting head from this experiment can be considered as success. So, probability of x is equals to 1 is nothing but p. Whereas probability of x is equals to 0, meaning the probability of getting tail is failure, which is 1 minus p. These results can be obtained from the following probability mass function, from this one. Passing or failing a test can be considered as a Bernoulli trial, right? Passing or failing a test can be considered as Bernoulli trial. The customer buying or not buying a product can be considered as Bernoulli trial. Yes, no responses of respondents of specific question can be considered as Bernoulli trial. All such trials H can be generate this probability mass function for x, which is distributed Bernoulli with parameter p, has a probability mass function given using this one with possible values 0, 1, where 1 represents success, 0 otherwise for the failure. This probability of success is denoted by p here, 1 minus p, probability of failure. For this probability mass function, we can summarize it using mean and variance, where the mean is p, the variance is p minus p. This can easily be computed from this table, for example, probability of x, right? The possible values of Bernoulli distribution 0, 1. So what's the probability of x is equal to 0 is nothing but, right, making this one 0, then probability the power of 0, 1 minus p the power of 1 minus 0, right, is nothing but 1 minus p, 1 minus p. And the probability of x is equal to 1 is p. We put 1 here, we put 1 here, 1 minus 1 is 0, 1 minus p the power of 0 is 1, then we left with p. Therefore, the probability of x equals to 1 is p. Recall that expected value of x is given by x probability of x for discrete random variable. So x, when x is 0, 0 times probability of 0, 1 minus p, plus, right, 1 times p, right? Therefore, this is 0, 0 plus p is p. Therefore, expected value of x is nothing but p. Similarly, this variance can also be computed to be p into 1 minus p. The other way of fitting a random experiment with two possible outcomes, but for an independent Bernoulli trials, is nothing but binomial models. This binomial distribution models the number of successes in n independent Bernoulli trials, right? This counts how many success occurs in n trials. Here was the assumption: in binomial distributions, the same probability of success in each trials, and each trials are independent. Examples for which Bernoulli distributions can be modeled is number of heads in 10 coin tosses, number of defective items in a batch, number of customers purchasing out of 100 approached, right? So here for binomial, n should be greater than 1, right? These trials should be independent, right? Independent. This n trial should be independent. P should remain constant or fixed from trial to trial. Under this assumption, a binomial random variable x counts the number of successes in n independent Bernoulli trials and generates this probability mass function given values 1, where the possible values are 0, 1 up to n, right? Where x is the number of successes here, k specific number of successes, how many possible values, 0, 1, 2, n. We can compute the probability of x is equals to k, where k is this one, or this one, or this one, or this one, right? And each total number of trials. Tossing a coin twice is all about probability binomial distribution, right? If a coin is tossed once, this is about the Bernoulli distribution, right? So Bernoulli distribution is the base or the building block of binomial distribution. We can say probability of success in each trial, p, 1 minus p, probability of failure, where this combination is number of ways to choose x successes from n trials with mean np, variance np into 1 minus p. So this is all about binomial distribution under these assumptions. Let us see examples about binomial distribution. Tossing a fair coin 3 times is a random experiment, right? Random experiment is a base for all in probability we mentioned so far. So what's the probability of getting exactly 2 heads, or what's the probability of getting outcomes with 2 heads is a question here. So as the first step in solving such problem is to identify what is n, right, what is p, and what is the x, right? For x, which is random variable distributed binomially, right, with parameter n, p, we need to first identify what is n and what is p in practice. So here from this random experiment we can understand that the number of trials was 3, meaning n is 3. In each trial, what's the probability of getting head? Wow, p head is 1 over 2. The probability of tail is 1 over 2. So p is 0.5 here. Now the required number of heads is to be 2. Therefore, probability of x is equal to 2 from the probability mass function of x following binomial distribution is given by this one, right? 3 is n, 2 is x, n combination 2x, 3 to 2. Then this one is p, this one is q. Then we come up with this at the end of the day, 0.375. So the probability of getting outcomes with exactly 2 heads is 0.375. We can interpret this in probability in percentage too. There is a 0.5 chance of getting exactly 2 heads in 3 tosses of a fair coin. Yeah, this problem equivalently can be solved from the immediate random experiment counts. This tossing a coin 3 times generates the sample space, right? H, 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 T, H, T, T, right? T, H, H, T, H, T, 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 H, right? 1, 2, 3, 4, 5, 6, T, right? H, T, H, Z, 1, 2, 3, 4, 5, 6, 7, T, T, T. These are the actual outcomes from tossing a coin 3 times. From this, what is X is number of heads, right? Number of heads in each outcome. So, what's the possible values of this random variable? So, each outcome can have 0 head, or 1 head, or 2 heads, or 3 heads. These are the possible outcomes, right? This is one. So, what's the question here? Equivalently, what we have mentioned above, X is equals to 2. This is nothing but the probability of getting outcomes with 2 heads. How many outcomes are there? Here, 1, THH, these are the 2 heads. From this one, 2 heads, H, H, right? From this, we do have HH, right? 2 heads. So, one possible outcome with 2 heads, second, third. We do have 3 outcomes with 2 heads divided. How many outcomes? 1, 2, 3, 4, 5, 6, 7, 8 over. This is nothing but 0.375. This can be changed into 37.5% of getting exactly 2 heads, right? But what's the difficulty of this way of solving probability when the number of trials gets large, right? If n is increased into 100, right? N in the previous example was 3, meaning the tossing a coin was 3. But what if n is tossed 100 times and the question is similar, the probability of X is equal to 2? This becomes difficult to solve through this way, right? So, following the probability distribution for large number of trials of experiment is important. Another example, suppose a student guesses a 4 multiple choice questions, each with probability of this one of being correct, right? We want the probability of exactly 2 correct questions. What we want here is the probability of exactly 2 correct answers, right? And a student was provided with 4 questions, right? 1, 2, 3, 4. So the student can answer 4 of them, 3 of them, 2 of them, 1 of them, none of them. But the possible values of this random experiment is that the student can guess all questions correctly, right? Can answer 3 questions correctly, can answer 2 questions correctly, can answer 1 question correctly, or can answer no question correctly. So what's the probability of this one is the question here. The probability of exactly 2 correct answers are. This can also be solved using the binomial distribution, where number of questions or number of trials is 4 here. P is given. The probability of getting correct answer in each question is 0.5. Probability of correct guess. X is 2. Then we simply substitute to their respective relevances in the probability mass function of the binomial distribution, right? With 4, 0.25, where X is now binomial with 4 number of trials with probability 0 to 5. Therefore, we come up with this result, right? So there is about a 21% chance the student gets exactly 2 correct answers out of 4 by guesses. Let us proceed to the Poisson distribution. Poisson distribution can be modeled to such as number of phone calls per hour, number of email per hour, number of accidents at an intersection per month, number of printing errors per page, meaning that Poisson distribution is used for counting events in a fixed interval of time or space, right? For an interval of hour, what's the probability of getting phone calls, for example, 2 calls, 3 calls, 4 calls, 5 calls, or no calls per hour? These are the possible outcomes here. 0, 1, 2, 3, 4, meaning no call per hour, 1 call per hour, 2 call per hour, 3 call per hour. The same is true number of emails per hour. So what's the domain here is time or space, right? In which we count the number of events. Apply when events occur randomly, but with a constant average rate, which is lambda. Now X is Poisson distribution, right, with lambda, where lambda is the average rate of occurrences, right? Average rate of occurrences. This is suitable for modeling rare events occurring independently over time or space. For example, these events are occurred per this interval of time, hour. The number of emails per hour, this is time. The number of accidents at an intersection per month, this is time and space, right? Number of printing errors, this is space, right? So a Poisson random variable x counts the number of events in a fixed interval of time or space with probability mass function given this one, where x is number of events. Now x is the specific number of events when k is 0, when k equals to 1. We are talking about the specific number of events, whereas x is the number of events that collectively consists of all possible values, right? This lambda average rate of occurrences, mean number of events per interval, where this one is constant with this number x factorial of x is given by 1, and from this probability distribution we can find also this mean with lambda variance lambda order. Let us see simple example. If the average number of phone calls per hour is this one, what's the probability of receiving x in an hour? Here lambda is 3. The average number of phone calls per hour is 3 from experience or from prior knowledge. Now what's the probability of receiving exactly 2 calls in an hour? We recall this formula, right? Lambda is this one, 3. This exactly 2 is about k. Everything other is known. Therefore we come up with this result, right? After substitution, probability of x is equals to 2. This one is this one. If average is 3 events per day, find the probability of exactly 1 event, right? Lambda is 3. The number of events desired is 1. By substituting we come up with this result, right? Therefore there is about 15% chance of observing exactly 1 event in a day, when the average rate is 3 events per day, right? It is too simple. What the important thing is when to use each probability distributions to model.